All right. Good. So today we will learn about the Euclidean formulation and its relation to finite temperature in quantum field theory, which will be a better way of describing quantum field theory, as I will show you. But before we get to that, we need to finish what we started last time, which was to consider the path integral in the harmonic phase space, and to see how from that we get the correct boundary conditions. Let's remember where we ended up last time. So last time we defined states alpha that were the eigenvalues, eigenstates of A, of the creation operator, with eigenvalue alpha, and then corresponding alpha star that were daggers of this. And then we considered Heisenberg states. And we defined the transition amplitude between them. Called alpha, m of alpha star t prime alpha t. And then we've proven the fact that this was a path integral in the same way as we did for the usual configuration space path integral. Just so now the path integral was over d alpha star, and then here we have alpha dot star of tau, alpha of tau divided by I minus the Hamiltonian integrated over the time tau, and then plus the boundary term alpha star t alpha t.
So this path integral has that the configuration space in the
Yeah, we'll get to that. Yeah. We'll get to that. I mean, the specific issue we wanted, right, was the definition, the correct definition of boundary terms, right? So remember we did an analysis in configuration space, and we came up with the fact that the correct path integral had an extra boundary term, but the proof that we reached was not completely rigorous, and the one we do in here will be more so. Let's see why. All right. So here we've defined states alpha and alpha star, and I emphasize also by the fact that we integrate separately over alpha and alpha star, that these were thought as independent variables, right? But then the issue comes, what are the boundary conditions for this? What are the boundary conditions imposed on these path integrals? So I have to say something about alpha of t and alpha prime of and alpha star of t prime. So let's say boundary conditions alpha of t, alpha star of t prime. Now, if we're talking about some classical path, then obviously we could, in principle, define whatever we want for both alpha t and alpha star of t. Sorry, I should say alpha star of t and alpha star of t prime and alpha of t prime. So we could in principle do anything that we want. However, in quantum mechanics, so classical mechanics, anything is allowed. But in quantum mechanics, that's not necessarily so. Remember that these alpha and alpha star defined at some time t are defined as eigenvalues of some operator, right? In this case, operator A and operator A dagger. And we have, in quantum mechanics, we have a general theory that says that if we have two operators that do not commute, so A, B commutator is different than 0, then we cannot define them simultaneously with arbitrary precision. We can't give their eigenvalues simultaneously with arbitrary precision. This is a statement that goes under the name of Heisenberg uncertainty principle, right? Perhaps generalized uncertainty principle. Right? So of course, the name, specifically the name Heisenberg uncertainty principle, is reserved for operators P and Q, which don't commute. And then I can give their eigenvalues P and Q only with an uncertainty delta P delta Q. But as you know, this is a general statement. So if one defines the uncertainty in the eigenvalue of A by saying that delta A squared is by definition in some state psi, is the average in the state psi of the operator minus some average value A times 1 squared then we know that the theorem that goes under the name of Heisenberg generalized, perhaps generalized Heisenberg uncertainty principle, is that delta A times delta B is greater than 1/2 in the same state psi of I commutator A with B. Well, okay, it's H bar, but this is equal to 1. Right? So the case that we're most used to is, as I said, P and Q, right? So let's say QP equal to IH bar, and then delta Q. Oh, sorry, nobody corrected me. This should have been absolute value squared, right? It doesn't matter the sign, for instance, of the commutator. So delta Q delta P in this case is greater or equal than H bar over 2. Right? Okay, so this is a general statement, but now we have to remember that in our particular case we also have this to be true because A and A dagger don't commute. So commutator of A and A dagger is 1. So that means that that means that the uncertainty in alpha and alpha star is bound by Heisenberg uncertainty relation. Of course, so in this Heisenberg picture, we define things at certain times, so this would be only when we're talking about alpha at the same time. So the time the time in here refers to the fact that states at different times are different states, right? In the Heisenberg picture, operators evolve, but the states don't evolve, but correspondingly states at different times are different states. And then specifically with respect to our issue of boundary conditions, so we have to define alpha of t and alpha star of t, and also alpha star of t prime and alpha of t prime. Right? But because of the uncertainty relation, I cannot give both of these things with arbitrary precision, neither both of these things with arbitrary precision. If I want to give something with arbitrary precision, then the other one is completely free, right? So delta, let's say delta alpha is 0, delta alpha star is infinite, right? And that is what we're gonna choose, namely so at t we want that alpha of t is alpha. We want this to be true. But then that means that alpha star of t is free, unspecified. And that t prime, we want conversely alpha star of t prime to be alpha star. That means that alpha of t prime is free or unspecified. Okay. The thing in the exponent of the path integral, the thing, excuse me, the thing that therefore minimizes the path integral, that gives correspondingly the classical values, deserves the name of classical equation of motion. So we will call would say that we have classical equation of motion defined by the variation of the exponent in the path integral. I hesitate to call it action because it's not really, I mean, at this point it's not defined as an action per se. It was in the case of the usual phase space, it was an action. In the case of the harmonic phase space, it's not clear that it's an action, but it will give still the classical equations of motion. So we get what? So let's say we vary first with respect to alpha star. And then we get, so with respect to alpha star, I need to partially integrate. I get a minus sign, then alpha dot of t, of tau, sorry. And I want to multiply it on the other side, so say dh d alpha star 0. And then I can put plus if I want to. And then I remember that h was for us omega a dagger a minus j of t a dagger, right? That was, yeah, that was the definition, minus j of t a dagger minus j bar of t a, right? This was this was the Hamiltonian in the presence of driving force. So this was as an operator, and then when I replace, when I do the path integral, remember this was where I replaced a with alpha of t and a dagger with alpha star of t, or tau, whatever, inside h, right? So that means that h of alpha star t is omega alpha star tau, alpha of tau minus j of tau alpha star of tau minus j bar of tau alpha of tau, right? So when I take the derivative with respect to alpha star, derivative with respect to alpha star is omega alpha of t, of tau, minus j of tau, right? So the equation of motion here would be alpha dot of tau plus I omega alpha of tau minus I j of tau equals 0. And now, yeah, exactly the wrong thing. So here I had alpha star dot alpha over I minus h. So now I do the same for the variation with respect to alpha. right? So with respect to alpha now I get alpha dot star of tau minus I dh d alpha tau equals 0, right? Which is indeed just the complex conjugate of this one if alpha star is the complex conjugate of alpha. So that's good. And now similarly I find that this thing dh d alpha of tau is omega alpha star of tau from here, and then from here minus j bar, minus j bar of tau. So finally, the second equation is, again, I could have derived it by just taking the complex conjugate, assuming that alpha star is complex conjugate of alpha. So get alpha star dot of tau minus I omega alpha star of tau plus I j bar of tau equals 0. Right? These are the equations of motion. And now I can find classical solutions of this. And the classical solutions be this. Sorry, T minus tau plus I integral T tau 1 omega S minus tau J of S ds. Now the classical star tau star E minus E I omega tau minus P prime tau plus I integral from tau to T prime E I omega tau minus S J bar of S ds. So here I'll specifically drop a few steps because this is an exercise for you, but I mean, it's kind of not very complicated. So once you see that this is a solution of this, which you can kind of understand, I mean, this is just a linear equation, you just integrate it, it's not complicated. And then this is kind of like the complex conjugate of the other if alpha star is conjugate of alpha. And then moreover, you can plug that back in and calculate this exponent in here. So the exponent was of this thing. So calculate the exponent. The exponent, I cancel, it was alpha dot star of tau alpha of tau just a moment. Well, okay, let me So specifically, it was the integral of this thing minus IH, then plus alpha star of t, alpha of t. So this is the exponent that we're trying to calculate. And the final result that one obtains, which you should prove, is this. Okay, so this is the result. I mean, it's some algebra which you can do, it's not a big deal. But the point I want to emphasize here that you get, you see, this first term is quadratic in the alphas, in the boundary conditions. Then in here, I have a linear term, also in here, right? And then finally, this term is independent of alpha and alpha star, right? So I have a quadratic, a linear, and a constant term in terms of alpha and alpha star. All right. And because this is quadratic, and the path integral, which again I erased in here, but the path integral was integral d alpha star. Right? So in the path integral, I have these terms, which are, as I said, quadratic, linear, and constant. So that is also of the type of a Gaussian integral. So it's really the same kind of logic that we did last time in the configuration space. So one can also write then well, one can also write that alpha of t, the variable of integration, is alpha classical of t. So I should have said this is calculate the exponent on the classical solution. So this was the classical exponent, which is the minimum of the minimum of this value, the minimum of the exponent is also given, is also a quadratic term. But what I mean is that in the path integral itself, I separate the value of integration, alpha of tau, in terms of the classical value of integration, alpha of tau, and the quantum fluctuation, the same way as did last time in configuration space. So this is the variable, let's say classical solution, plus an alpha tilde of t. That's a quantum fluctuation, right? Corresponding to alpha star class. All right, and then as before, I don't need to repeat because it's really the same logic. as before, we shift the path integral. So from alpha of t, alpha star of t, now to these alpha tildes, right? And correspondingly, you find that this exponent, that I'll call E, just for to have a name for it. So the exponent, before it was an action. Before I wrote just S, but now it's not an action, so I'll call it just exponent E of alpha of t, alpha star of t, and sources. This is now like before, the exponent on the classical solution, classical exponent, which I've calculated here. So let me call this now. So this is now E of alpha of t, alpha classical of t, alpha classical star of t, gamma bar. Okay. Plus the exponent that depends on the fluctuations. But with no sources, right? And so, as before, we get that the path integral, call it m, right, was equal to some constant meaning independent on the variables. The variables in this case being alpha and alpha star. Remember, the boundary conditions are given in terms of alpha and alpha star. And they also depend on j and j bar. J and j bar. Wait, why did I call them gamma? Did I call them gamma before? I think I changed myself. Change the notation.
Later you say that gamma is j over root 2 over in the final line of the same page.
Do I say that? Let's see. Yeah, I have different. I have notes that I'm already modified a little bit. So, I think. No, it's J. It's J. I changed notation. That's all. Remember, I called them J, and then I wrote that the relation between the configuration space J and the harmonic phase space J was given by square root 2 omega. So it's just. And this is already in the book. Bad, but anyway, I hope it will be clear to the reader eventually. But I just changed notation from J to gamma. All right. So is a constant times this exponent. So exponent e to this e of alpha classical of t, alpha star classical of t, j and j bar. Okay. And you note here we had a constant piece. This was independent. No, sorry. The other way around. So I can yeah. So if I want So this thing depends in principle on alpha, alpha star, J and J bar. However, most of the time we'll not be interested in the conditions, we'll mostly be interested in the dependence of J, right? And then we have the opposite. So these things are linear in both boundary conditions and in sources, but then this is quadratic in boundary conditions and constant in sources, this is quadratic in sources and constant in boundary conditions. So if I consider only the dependence on J and J bar, then I can include this first term that is independent of J and J bar. I can include it in N, right? And then I will get from this exponent, like in the case of the configuration space path integral, I'll get a term that is quadratic, this one, and which we'll see that obtains just the usual term we got some time ago, right? And then we also obtain a term that is linear, which was the boundary term that we've obtained in configuration space last time, the extra boundary term that we obtained. Okay. All right. So let's see how do we relate this calculation to the configuration space calculation. Well, the first thing, we would need to have vacuum states at the ends. We need to have vacuum states at the ends, right? But now, as things stand, we have something with eigenvalue alpha, and on one end and alpha star at the other end. And remember, these are coherent states. I mean, yeah, they're states that come with exponent alpha a dagger acting on 0. So the way to deal with that is obvious. So since this was equal acting on 0, we see that if I put alpha equal to 0, I get actual vacuum, right? So I have, if I choose alpha is 0 at t and alpha star is 0 at t prime, then I do get this vacuum, right? That means then I get 0 at t, then 0 at t prime. And then it remains the last step to take the time to infinity, and so t prime plus infinity, t2 minus infinity, right? Which is, because what we're interested in is the amplitude for a sufficiently long time. And so then we will call the corresponding amplitude, so then call n by z of j, and then I also assume now that j is real. So j is equal to j bar. That means little j is equal to little j bar. Okay. And then this path integral then becomes the vacuum at plus infinity. Remember, these are Heisenberg states. And the vacuum at minus infinity, both of them in the presence of this source J. And then we will get an exponential. And here, you see this form, so this is now equal to capital J of S, the square root 2 omega, and this J bar of S prime, square root 2 omega. Okay, so I have an integral over S, J of S, an integral of S prime, J bar of S prime, and then something else, right? So this is of the type, and also I have minus 1 in front, so of the type J dot some delta, I'll call it delta F because as expected this will be just a Feynman propagator, J. Remember, this product meant exactly that, double integral. Integral ds, integral ds prime, J of S prime, then delta F of S and S prime. Okay. Then we also needed, in principle, I didn't put that in the notes, but we had to remember that part of this was actually both infinities were times 1 minus I epsilon, right? So if I put this times 1 minus I epsilon, I should get rid of also the linear terms. Let's see if I get this right. Yeah, so I get e to the I omega t. But for t, I substitute minus, then infinity, 1 minus I epsilon. And so I get this term in here, e to the minus I times minus I is minus omega infinity epsilon, which goes to 0, right? So these terms go to 0. And this is, this is the regular integral. Right? This thing goes to 0 though. And this is a constant, okay? So in this case, I get just a quadratic term, and then the constant, I write it like this, meaning that this is the value of the same partition function when I put j equal to 0. Right? This is z of j equal to 0. Right? So I can define this normalization constant as the value at j equal to 0. And then, why do I say delta f? Because what we obtain here is e to the minus I omega to the value s minus s prime divided by 2 omega. Delta f is e minus I omega over s prime, s minus s prime over 2 omega. This was indeed the Feynman propagator as we've shown before, right? And how about the boundary condition? So we obtained what we found in configuration space. How about the boundary conditions? Well, we've seen that the boundary conditions, so at t going to minus infinity, because alpha t is 0, alpha star of t is free, and then at alpha star t prime is 0, and alpha of t prime is free. at t prime going to plus infinity, right? These were the boundary conditions. But what does this correspond to? Well, this corresponds to so this means there's no annihilation part. Alpha is the eigenvalue of A, but there is an arbitrary creation part. So this is arbitrary creation, so pure arbitrary creation part. And here, correspondingly, alpha is 0, no annihilation. Alpha, sorry, is 0, no creation part, but alpha is arbitrary, so pure arbitrary annihilation part. But on the other hand, what does that mean? You remember that Q was integral, but more importantly, e to the minus I omega t plus a dagger e to the plus I omega t, right? So pure arbitrary creation part means this term. So that means Q of t going to minus infinity behaves like e to the plus I omega t. And then Q of t going to plus infinity, Q of t prime going to plus infinity, pure arbitrary annihilation part, this thing, so this goes like e minus omega t. So these were indeed the boundary conditions that we found in the configuration space.
So this is the free solution, right?
I'm sorry?
This is for the free harmonic oscillator, right?
Yeah, this whole analysis was for the harmonic oscillator, yeah.
I can't see how you get this behavior of infinities.
No, this is for harmonic oscillator. Everything we're doing was for the harmonic oscillator. We didn't have any interaction, right? When you have an interaction, I cannot do the path integral explicitly, right? This whole thing was for the harmonic oscillator. Remember, this is the story. If you understand the harmonic oscillator well enough, you should understand everything. So we're just doing the harmonic oscillator. And last time we found that the boundary condition was this, that we had to restrict to Q's that went to plus infinity, that went at minus infinity to e minus omega t, e plus omega t, and at plus infinity to e minus omega t, right? In this way, we avoided the classical solutions, which were the zeros of the Q, the zeros of the kinetic operator acting on Q, right? And then we could invert that kinetic operator, obtain delta. All right, so that was the end of this analysis. So we see that with a lot of work, we were able to obtain a correct analysis, including boundary condition and all, in real space, in Minkowski space. However, in general, that is difficult, and so what one does usually is to define the so-called Wick rotation to Euclidean time. And we will see that when we do this, we find a connection with the statistical mechanics. Specifically with the partition function. So, this was all for the harmonic oscillator, which is quadratic. I can do it exactly. However, in more general cases, what one needs to do, we have some complicated action, which is, I don't know, cubic, I mean, polynomial or whatever, not even polynomial. Then, in general, what one needs to do is to use the so-called saddle point approximation. So this is, the saddle point approximation can work for any integral, but in particular, the path integrals we're interested in, they're already of the type integral over an exponent of something. So if you do that, then, so something like integral of something, then exponent of some action. Then the saddle point approximation is writing that as its extremum value, which in the case of an action is the classical action, plus quadratic fluctuations around it. And then, of course, in principle, they're higher order terms, right? But the approximation is keeping just this, right? Which is pretending it's kind of 3, right? It's pretending it's just the classical part plus a harmonic oscillator-like piece, quadratic piece, right? You can always do that. That's just a Taylor expansion. The issue is whether or not these terms are really small. But in principle, you could always do this. So again, for the free action that we considered, the saddle point approximation is just exact. There's nothing, no approximation. But in general, when you're talking about an interacting theory, this is an approximation. However, there's one more trick. I mean, we've actually, in all the things that we did, we acted as if we're doing something correct, and we did a Gaussian integral. But the Gaussian integral, remember, it's actually something of this type, which is well defined because this drops exponentially fast at both ends of the integral, right? But the case that we are interested in is not like this. The case that we're interested in is of a real action with an I in front. So the exponent is always imaginary. Right? So our case is of this type. Well, with a plus and minus, it doesn't really matter. The point is there's an I. Right? Yeah, perhaps let's just let's say it's with a minus. But as I said, it doesn't matter. And then, of course, this is much less well defined, right? This is oscillatory, right? So if I integrate between, if I put a cutoff lambda, right? Then the difference between this and the one with a modified cutoff by a finite quantity is finite, right? Doesn't go to 0. So this is much less well defined, right? And on top of that, of course, what we have here is a path integral, which is really an infinite product of integrals, right? Right? So that is, on top of that, there's even less well defined, right? So because of this, you know, we've acted as if we're doing things correctly, and you know, we had to go through a lot of steps to make this kind of correct. But you always have to keep in the back of your mind that we nevertheless used formulas for Gaussian integration that were not obviously well defined. Okay? And of course, then the solution would be if there would be a way to have something like E minus S to have actual Gaussian integration, right? Because then S will have a minimum, and then I can use this quadratic approximation, and I would actually get a Gaussian integral. And that is the point of this Wick rotation to Euclidean time. So the Wick rotation is a procedure to go from Minkowskian space to Euclidean space, such that we go from e to the is to e minus s, and we can do Gaussian integrations. And by extension, by using the saddle point approximation, we can do any quantum field theory. So this procedure is Wick rotation to Euclidean space. Okay. And then how we do, well, let's see how we do this. And let's start by understanding what happens in quantum mechanics. That's our case. So let's consider a Hamiltonian that is time independent. That's anyway the standard case. Time independent Hamiltonian is more difficult. And then that it has a state, a set of eigenstates n. Basis of eigenstates, complete state. Okay, so that means complete set means we can write this. And moreover, let's define the energy to the positive. I mean, that's a good system, is bounded from below, and then we can always define the minimum energy to be positive. And then the amplitude that we're interested in, the product of Heisenberg states, is written in terms of the Schrödinger states as usual with evolution operator E minus IH times T. So this is now in the Schrödinger picture. But now, because because we have a complete set, we can insert here and here. Right? And write this as Q prime n, or over n and m. And then, and then n e minus I h t minus t prime minus t m n q. Right? And then I should have said also orthonormal states. Meaning nm is delta nm. That's easily found. And then when this acts on the state, gives an energy. And then n times n gives delta nm. So this reduces to a sum over n q prime n, e minus I e n e prime minus t, n q, right? So this is what we call the wave function of the state n in the configuration representation, right? Psi n of q prime. And this is complex argument, so psi star n of q, right? So our amplitude is equal to sum over n. Here psi no, let's write like this. Psi n of q prime, psi n star of q, e minus I e n t minus t prime. Right? And now let's see what the effect on this what the effect on this is, let me call this delta t, of the Wick rotation. So remember, the Wick rotation means that I have to go from Minkowski to Euclidean time, and specifically the rotation is time goes to minus I beta times the Euclidean time. And in the case of the variation in time delta t, I call that Euclidean variation beta for a reason which will become obvious immediately. Then I can shift this t, is irrelevant, I can put t equal to 0. And so what we're calculating is this thing. So now this is in Euclidean time. So we have psi n of q prime, psi n star of q. But now minus I delta t goes to minus I and minus I, which is minus. So minus beta en. Okay? And now we observe that if I put q prime is equal to q and integrate over q, what we'll get is the partition function of statistical mechanics. So integral dq, q beta, q0 is integral dq, sum over n, psi n absolute value of q squared, e minus beta en, right? So this thing is also known as trace e minus beta h, right? And so this is called the partition function. So by adopting the same nomenclature as in statistical mechanics, we will from now on call this kind of amplitudes also partition functions. So this is a trace because it's sum over the eigenstates, right? Then with the probability to be in that eigenstate, probability being integral dq of absolute value psi n squared of q squared. So this is just trace e minus beta h. This is the partition function of statistical mechanics. And then, more importantly, we know that that beta is 1 over kVt, right? So time, note, time has gone to minus I beta, where beta is 1 over kVt. So time has been replaced by temperature. Okay? Alright, so now let's think a little bit about what we did. What we did. So we've considered closed, because q prime is equal to q, Euclidean paths, q of t, q of tau, closed Euclidean paths of time length beta is 1 over k dt, right? So this is actually q of t prime, which is t plus beta. This is t prime, and q is at time t, right? Q prime t plus beta is q of t. And well, I shouldn't say t, I should say tau, or better t Euclidean, right? Because I already Wick rotated, so t and t prime were notions in Minkowski spacetime. Now I have, I should have called them really tau. Not t Euclidean, that's fine, t Euclidean, it's clear. Okay. All right. But then let's see what happens to the path integral itself. So the object we're calculating, this thing, the way we've written like this was an operator statement, I mean states, but then we had written it in terms of path integral. So let's see what happens to the path integral. So we had the Minkowski Lagrangian q dot squared over 2. Yeah, perhaps let's write more precisely like this: dq dt minus d of q. Okay. And then in the exponent we have is, I times the action. And now let's substitute with this Wick rotation, right? So let's substitute the value of the action, taking into account this Wick rotation from t to minus I beta. So, from t to minus I t Euclidean, I call it t Euclidean, right? Then delta t minus I beta. Okay, so here I have dt. So now I write instead minus I dt e, right? And then the integral over t e is from 0 to beta. Then I have this Lagrangian, and I have 1/2 dq. It's just that now I need to replace t again with minus it, so minus I dt squared minus d of q, right? Okay, now minus I squared gives a minus 1, okay? And then this thing then I with minus I cancels, and minus I squared gives a minus 1. Okay? And note I have minus in both terms. Right? Now I want this was my goal in obtaining the Gaussian integration. I want to replace e to the is Minkowski with e to the minus is Euclidean. Right? So I want to define this as minus is Euclidean. Q, which means that S Euclidean of Q. So remember, I had the minus sign in both terms, so that came out, and this is this minus, and everything else is my action in Euclidean space. So this is integral 0 to beta dt e, and then 1/2 dq dt e squared plus d of q. And then, of course, this is what I will call the Euclidean Lagrangian. Okay? And note an important thing, whereas the Lagrangian and correspondingly the action was not positive definite, it was a positive part minus another positive part. Now this is the sum of two positive terms. This is, well, I mean, bounded from below. V I can define to have negative energy, but in any way it's bounded from below. So, so this is really what I want. It's E, now I have E minus SE where this is positive, SE is positive, or at least bounded from below. And and so finally, when I put these two informations together, I get that Z of beta, which is this trace E minus beta H, is, so this was the integral of a dq times this amplitude, which was what I obtained in my path integral. But I will write this as just one path integral. And then I have to remember what I had. I had that these were closed paths, so Q of T Euclidean plus beta is equal to Q Euclidean, so closed paths, right? And then I had the integral of a dq, but anyway I have a path integral here. So all I have to say is all closed paths, right? Integral of a dq is just one of the integrals of the path integral, right? So I choose a closed path, right? And path integral means I integrate over all of these points, right? Normally I would not integrate over the initial and final point, but now I also integrate over the initial and final point because it's just one or more of the points on the closed path, right? So this is the closed path of time length beta. Okay? And this is called the Feynman-Katz formula. Okay? So now we have a very important relation, as I said, between statistical mechanics and quantum field theory, specifically quantum field theory in the path integral. All right. All right. Moreover, now I can also use, so until now I've shown to you that I've argued that there were correlation functions that were interesting observables, and I put them together in the generating functional that I called Z of J, right? And it was, you know, not a coincidence notation. I had in mind this kind of partition function. But now, knowing this connection to the statistical mechanics, I know that this object contains all relevant information. So we know from statistical mechanics that all relevant information is contained in the partition function with sources. So thermodynamic, specifically thermodynamic information is encoded in the dependence on beta. And if I want some other information, I can add sources. So this is what we'll do. We introduce J of T's. And then I define z of beta and j as integral dq e minus Euclidean action depending on beta plus this integral dte je, sorry, d tau, let's say, and dte, te, qe of te, right? And also, so you can take this as a definition if you want, but then you could also check that this is the same. So before we had this term, right? And now I just decrotate it. And then j of minus I te, q minus I te, right? And I minus I cancel. And then I have to just define this as je of te, and this as qe of te. Right? And then a very simple quantity is the second derivative, which will give the propagator in this imaginary or Euclidean time. Yeah, maybe I couldn't call it tau. It's too many letters. Tau 1, tau 2. So just as usual, when we have this, we've added the source term in the exponent, then the point we remember is that you take the second derivative, for instance, you divide by the normalization, and then you put j equal to 0, and you obtain just dq of tau, q of tau 1, q of tau 2, e minus se of beta, then 1 over z beta, right? Okay, then we remember that this was that the initial initial formula in Minkowski space before this big rotation was related to a transition amplitude, right? So this thing was nothing but the time order correlator. So in the vacuum state, so we had T of Q minus I tau 1, Q minus I tau 2, omega, right? This is the Wick rotation of the correlator, okay? So this is equal to, that integral from before is equal to this. But But now, so really what we did, so the only thing that changes in the Feynman-Katz formula and its derivation is the introduction of these things. So this is 1 over z of beta, trace E minus beta h times t of q minus IT1, q minus IT2. Okay. And then the only thing, these are operators now. So so the q of t introduced inside the path integral was just a classical value. But when I talk about the operators, I have to remember that these are evolved with the Hamiltonian. So q of t would have been e to the I h t, q e minus I h t, right? But then that means that q minus I of minus I tau, I just replace this in here, right? So minus I times minus I plus, so I get e to the h tau, q e minus h tau. Okay. And one issue that we still have to think about is what about time ordering in Euclidean space? Well, so the time order, you have to remember, the time order, strictly speaking, applies only in Minkowski space. If I go, so time ordering, so only in Minkowski space. Why? Well, because only in Minkowski space this is a well-defined notion, where I have space and time. In Euclidean space, space and time are kind of the same. You can have a rotation. So time order is a less well-defined notion. So strictly speaking, time order should be defined in Minkowski space and then recrotated. You can loosely speak of time order in Euclidean space, but what you mean is really Minkowski. Okay, so that's a subtle point that now because of this periodicity with beta, you can in principle, so I wrote integrals from 0 to beta, but I can in principle extend it. So periodicity in beta means I can extend 0 beta to minus beta beta, for instance. Right? Because of the periodicity. So sometimes people do that as well. Then the propagator the presence of periodicity beta also should have the same periodicity. So delta of t, say plus or minus beta, should be equal to of tau, sorry. Should be equal to delta of the same tau. Okay? So that's a check of on any result that we should put. And so now about calculating the free propagator. Well, so of course I could calculate it from the path integral. I define the path integral, and then I could calculate it the same as we did before. But there's another way to do it. Is to remember that the free propagator, as described before, it was supposed to be a Green's function for the Klein-Gordon operator. So specifically, is a Green's function for the Klein-Gordon operator, which specifically means I take this operator and I act on it on this. So in principle, I call the Green's function k. That depends on 2 times t, tau and tau prime, and then this should be delta. And then the solution of this should be the free propagator. And then the point is that I left for you as an exercise to show that so there's a unique solution with the periodicity that I want. So with the periodicity delta delta free, let's say, of tau plus minus beta is equal to delta free of tau. So if I impose the corresponding periodicity on this equation, then there's a unique solution, and that unique solution is the following: delta free of tau is 1 over 2 omega 1 plus n omega e minus omega tau plus n omega e omega tau, where n omega is 1 over beta absolute value omega minus 1, which you recognize as a Bose-Einstein distribution. Okay? So this is an exercise to show. Okay, then let's also notice what happens when beta goes to infinity. When beta goes to infinity, I can neglect this, and then n omega is e minus beta omega, so it goes to 0 almost. And then I'm left with what? So these terms go to 0, and then I'm left with just this term, 1 e minus omega tau, right? So you get delta tau is 1 over 2 omega e minus omega tau. Yeah, well, for tau go positive, right? Yeah, tau positive. And then I recognize this. This I've written for you before. This is just the Feynman propagator for tau positive. For tau negative, I had the opposite sign. So in fact, for the propagator, I had this. But for tau positive, then I get just this. Remember, because the point is, I defined my propagator on 0 beta and extended it to minus beta 0 by periodicity, right? So there is no. I shouldn't expect this to hold for negative beta, because the negative beta was just an extension by periodicity, it was not definition of it. Right? Okay, but what is this limit? Well, beta is 1 over kBt. So this means T goes to 0. So this is the 0 temperature limit, right? And then, moreover, this amplitude, which we saw that was sine of q prime, psi and star of q, e minus beta m, en, right? In this limit, if beta goes to infinity, then I'm left with just a contribution of the vacuum, right, of n equal to 0. So this goes to just sine of q prime, sine star of q, e minus beta is 0, right? Psi is 0, I should say. So that's just the vacuum contribution. Okay, so that starts to look nice. So you see now, after doing the Wick rotation, not only have we defined connection of statistical mechanics, not only have we defined a well-defined Gaussian integral, but also now, by taking formally the limit beta goes to infinity, which means an infinitely long Euclidean time periodicity, which is to say no periodicity at all, but I mean, this has to be understood as a limit, right? In that limit, we're getting, in that limit, which is a 0 temperature limit, we're getting just a vacuum contribution. And that was really what we wanted to obtain initially in Minkowski space. We wanted to consider a transition from a vacuum state to a vacuum state, right? That was what I tried to describe until now, including at the beginning of the lecture, transition from vacuum to vacuum, right? So we are on the right track. Now we have obtained things correctly. And so in order to define our physical system, we have to consider infinitely long Euclidean time interval. But of course, in order to be physical, what we're interested in is that the physical part is a finite. So J of t has finite domain. Right? The sources have some finite domain. The interesting thing happens over some finite domain. And then what we obtain is a transition between two vacuum states. So we obtain a vacuum functional. Okay? Then we can say that the Euclidean path integral, the unrestricted, beta goes to infinity, so unrestricted, but remember this has to be understood as some sort of limit. Path integral is the vacuum is a vacuum functional. What else? Well, there's a couple more observations. So I said that because of the stat-mech connection, we call this z of j the partition function. Right? And then also by analogy with quantum mechanics, thermodynamics, minus log z of j, which will be called W of j, it's called free energy. Because in thermodynamics, the partition function is E minus free energy. So it seems like we did a lot of unnecessary legwork to get to a vacuum functional, but of course one can generalize this formalism in two ways. So the obvious one, which is going to be next lecture, is to quantum field theory. So quantum mechanics to quantum field theory. But the other one is I don't need to take beta to infinity. Beta to infinity will obtain the vacuum functional, and that was good. But I can keep beta finite, and then I'll get finite temperature QFT. However, that's not the subject I usually teach, but it will be in my book. So one can do much more using this formalism. You can define a full formalism for quantum field theory at finite temperature. Well, in fact, several formalisms, because there's not a unique one that works well. All right. So we did this for quantum mechanics, and well, it was implicit in all of this that we did it for the harmonic oscillator. But let's be more precise. So let's actually apply to the harmonic oscillator and see how we get a driven harmonic oscillator. So the path integral is integral dq exponent minus the Euclidean action. So as I said, the Euclidean action is integral dt, Euclidean, but I will not write Euclidean everywhere. And then dq dt squared over 2 plus v of q. That was the Euclidean Lagrangian. And then we want to add a source term, so j of t, j of t. Well, okay, so how about boundary terms? We did a whole discussion about what happens to boundary terms if you try to define the formalism directly in Minkowski space. Well, there are no boundary terms because we have closed paths. Problem solved. I'm sorry?
Isn't this part general to consider all the terms, not all closed, but closed?
No, what I said is that the path integral is over closed paths.
Yeah,
There's nothing that happens over not closed paths. Over not closed paths, nothing happens. It's not quantum field theory. It's something else. Okay. Quantum field theory is only about closed paths. We just derived it, right? There was no wiggle room.
We assume it closed paths.
No, we derived it. We derived it, right? We started from statistical mechanics and we derived closed paths. There was no assumption involved. Okay, let me do it again because it seems like. So we started with this, right? We started with this, and we wrote that this was equal to, if I put, no, this was equal to sum over n, psi n of q, q prime, psi n star of q, e minus beta en, right? And then I said that if I put q prime equal to q, and I integrate over dq, then I get here psi n q squared integral dq, which amounts to trace.
Yeah, but you assume q prime equal to q then.
I'm sorry?
You assume it.
Yeah, only for this I get this, yes. So I have to impose this, it means I derive it, right?
Yeah,
If I, otherwise,
but you at some point have to impose this.
yeah, if I don't get nothing. So the path integral over paths that are not closed means nothing. So I derive it, no? Because the path integral over closed paths means something, the one over paths which are not closed means nothing.
Yeah, but what I want to say that at some point you have to impose that.
Let's just think about it. Just think about it for a while and then because
if you consider every path is marginal,
then these other paths mean nothing. So only the closed paths mean something. Therefore, if the rather the closed path means something, the formula is one. Non-closed paths mean nothing. It's not the formula we want. Right?
How I can
just think about it. Just think about it for a while, and it will come to you. Okay. All right. So anyway, this is about Euclidean time, right? We're talking about Euclidean time. We're not talking about Minkowski time, right? Minkowski time, sure, I can choose any path I want. We're talking about here about Euclidean time, right? You understand that? Okay. So in Euclidean time, those were related to something in Minkowski time, only if I have closed paths, right?
Yes, no, I totally agree. The thing is not.
So you can define some crazy Euclidean time quantum field theory which has nothing to do with anything you observe, if you want, if you're a mathematician, and then it means nothing, but okay, you can study it.
I totally agree.
So, all right. Okay. So, so in this case, this path integral then is equal to integral dq exponent minus a half integral dt q of t. So now, as I said, we have no boundary terms. So I just partially integrate at will. So I can write in here minus dt minus d squared dt squared acting on another q. And then for the harmonic oscillators, this would be omega squared q squared over 2. So the operator is just minus dt squared d squared over dt squared plus omega squared acting on q. And then I still have the linear term j of t Q of t. So this is this is now quadratic as before, and as before I can do this Gaussian integral. It's just that now, first of all, there are no boundary terms, and you can have an exact Gaussian integration. So you can have an exact Gaussian integration. So the two problems that we had before of actually having an exponential that was oscillatory instead of decaying and having possible boundary terms are gone. And then I just get E plus a half times, well, J delta J, right? Specifically, I mean ds prime, J of S prime, and here I have the Euclidean propagator of S and S prime. So the Euclidean propagator of S and S prime is understood as just the inverse of this kinetic operator. This is minus d squared dt squared plus omega squared inverse, right? As a function of S and S prime. It's propagator because, as before, we wanted to understand the propagator as being the inverse of the thing that appears in the quadratic piece, right? And what does it mean, inverse? Well, we already saw it several times. It means you really go to Fourier space, where the differential operator is just a polynomial, and then you just invert in Fourier space, right? 1 over that thing. So this is integral d over 2 pi. Then 1 over, so this will be converted into e squared plus omega squared, then e to the I times S minus S prime. Okay? All right. So we had these two good features. There were no boundary terms. The Gaussian integral is done now exactly. There's no issue about what it means to do a Gaussian integral over an oscillatory object. But there's a third point. There are no poles anymore. This is an integral over a real variable EE. And then this thing, therefore, is strictly positive, right? So, by doing the integral in Euclidean space, we have found a well-defined formula without poles, which means this defines a good contour of integration. In the complex plane. So that means that really we should consider all physical quantities defined in Euclidean space. So define, calculate all physical quantities in Euclidean space, and then you must rotate. So the theory in Euclidean space had no ambiguities whatsoever. There were no boundary terms, Gaussian integration is fine, there's no poles. And then you reintroduce some of the ambiguity, but those are related to Wick rotation. So the Wick rotation is a priori could be problematic. So let's do this Wick rotation for the propagator. So the Wick rotation for the propagator is between Minkowski time t and Euclidean time s. Is t minus I s. T is equal to minus I s. Right? But then we want that its conjugate, the product with the conjugate variable, should be invariant. So that means Et should be equal to EE times S, which means that reversely now, the Euclidean energy is minus I times the Minkowskian energy. And so what does it mean to Wick rotate in here? Well, minus I can write it as e to the minus I pi over 2. Right? So this is a rotation by pi over 2 in complex plane. The complex plane. Right? But then, of course, if I would rotate completely by pi over 2, I'd get back to the original problem in Minkowski space, where I know that the poles are on the real line, on the real energy, real Minkowski energy line. So if I do a full rotation by pi over 2, I would get into trouble. So instead, I must do only pi over 2 minus epsilon rotation. That amounts to replacing this with minus I pi over 2 minus epsilon E. Okay. Then E minus I pi over 2 is minus I, as I said, and then E. But then this would be E to the plus I epsilon, that is 1 plus I epsilon, with multiplying E, so I can call this E plus I epsilon prime. This is epsilon E, right? And if I do this, then delta Euclidean of S equal IT is I integral dE over 2 pi minus infinity plus infinity. Then minus I E Euclidean S is E times T, as we said. And then in here we get minus E squared, because E Euclidean squared is minus E squared, plus omega squared. But then I had E, instead of E, I have E plus I epsilon. So then I get in here minus I some other epsilon tilde. Right? Okay? Alright, so this is P squared in a more general case of several dimensions, right? And then you notice that this is then nothing but the Feynman propagator. Okay? Now let's also draw some little bit of a diagram to understand what this rotation means. So the poles, so this is E, that is to say E Minkowski, Minkowskian energy. When the poles were at plus omega and minus omega on the real line, right? And then we went to Minkowski, to Minkowski energy. So in order to Euclidean energy, so in order to go from Minkowski to Euclidean energy, I have to rotate with plus pi over 2. So I have to go this way, right? So the contour of integration that I chose, so this is the Euclidean contour of integration. It's along the imaginary axis. And then Vic rotation meant going to this contour of integration, right? By an angle of pi over 2 minus epsilon. Okay? So the point is that then if I reverse the order of this, for instance, so I go from the integral to minus the integral, then I can close this, so yeah, I need to do it like this. I can close this contour like this, and see that within this contour, I have no poles, right? So the integral over CE plus the integral over the opposed contour, that is minus the integral over the real contour, is equal to 0 because there's no residues in the middle. That is to say, integral over the Euclidean and real contours is the same, but only if I do the rotation by pi over 2 minus epsilon. If I don't, I touch the poles, right? Okay, so again, now we see that the Feynman propagator comes naturally from rotating the contour of integration of Euclidean space. So it's not an arbitrary choice, it's the one that comes naturally by trying to avoid all the poles. Okay? And two more observations before I end. So one of them is that the puristic view of quantum field theory is that quantum field theory is defined in Euclidean space, and then Minkowski space is a Vic rotation of that. As we said today, in Euclidean space everything is much better defined. And then, so this is puristic in the sense of theory. So if you work in Euclidean space, things are easier to define, and then the difficult part is knowing how to Vic rotate. And then the other point was that I showed for you a connection to statistical mechanics, right? And I shown that you can calculate anything in statistical mechanics from the same path integral formalism using the Feynman-Katz formula. And there are several books that take this seriously, and I mean the most complete one I know is the huge tome by Saint-Justin. But so they take this seriously, and they treat quantum field theory as a formalism for both particle and statistical mechanics. But from now on, I'll just concentrate on particle physics. I'll just, have once in a while these comparisons to statistical mechanics, but will not actually calculate anything in statistical mechanics. But it can be done, so you can study this in parallel and use the same formalism. All right, so this is everything I want to tell you today. Do you have any questions? All right, so today, this was lecture number 8. So as I said, the first exam will be after lecture 11, so in exactly 2 weeks from today. So because of that, I'll give you by email and send you some practice exercises, because I know that most of you want to have something like that to test yourself. All right, so please go give me your exercises for today.